In this question statement of process heat transfer, consider a sealed 20 centimeter high electronic box whose base dimensions are 40 centimeter into 40 centimeter, which is actually placed in a vacuum chamber. The emissivity of the outer surface of the box is 0.95. The emissivity is actually represented by epsilon. If the electronic component in the box dissipate a total amount of heat which is equivalent to 100 watt, and the outer surface temperature of the box is not exceeded than 55 degrees centigrade, you have to determine the temperature at which the surrounding surfaces must be kept if the box is to be cooled by the radiation alone. Assume the heat transfer from the bottom of the surface of the box to the stand to be negligible. Let us just try to understand this question statement with the help of the diagram in the next slide. This is actually the box and it is being placed on this stand, right? And the dimensions of the box are also given here, that the height of the box is 20 centimeter, right? And the length into width is 40 centimeter and the 40 centimeter. And the electronic element which is present inside the box, which will dissipate a certain amount of heat, is 100 watt. The emissivity of this body which is placed on this stand is given as 0.95, and the temperature of this box will not exceed 55 degrees centigrade. It means that the temperature of this box is 55 degrees centigrade. So the heat will basically be dissipated or will move from this box to the surrounding by the radiation process, right? And it is given in the question statement that the radiation heat transfer from the bottom, right, from the bottom surface is negligible. So we have actually the 5 surfaces, right? So this is first surface, this is first surface, this is second surface, and similar to these two surfaces there are 2 surfaces which are on the back side, right? So these are 4 surfaces and the 5th surface is on the top. So heat is being transferred from this box to the surrounding by the only radiation process. So 5 surfaces are involved in the radiation heat transfer. So you are given with the dimensions of this box, you are given with the heat generation in this box that is equivalent to 100 watt, and you are also given with the emissivity of this box which is 0.95, and you are also given with this surface temperature which is 55 degrees centigrade. You have to determine the surrounding temperature, right? If you place a certain body at a particular distance in the surrounding, so what will be the temperature of that particular body, or simply you have to determine the temperature of the surrounding. Let us just try to understand this problem by taking some assumptions, like the steady operating conditions exist and the heat transfer by the convection is negligible. So we are not considering the convection heat transfer, we are only considering the radiation heat transfer. The emissivity of the box is constant and uniform all over the exposed surfaces. Number 4 is the heat transfer from the bottom of the surface of the box to the stand is negligible. What does it mean? We have only 5 surfaces. So the properties that we are going to need in the problem, in solving this problem, that is the emissivity of the outer surface of the box, which is also given in the question statement, which is 0.95, and it is represented by epsilon. So the first thing is that we have to determine the area of the box. So we have 4 surfaces, So the overall surface area of the box with the 5 surfaces, so 0.4, which is actually the converted parameter from centimeters to meters. All the dimensions which are given in the question statement, you have to convert it into meters, because it will help you to solve or to simplify the subsequent relationships easily. So after converting all the parameters or all the units which are given in the centimeters into meters, so you have to determine the surface area of the box. So 0.4 into 0.4 meter, so this part is actually the top surface area, right? And this is this part, which is 0.2 multiplied by 4, 0.4, 0.2 meter multiplied by 0.4 meter. The multiplication of this part is the area of one side of the box. When you multiply it with the 4, you will get the surface area of the 4 sides of the box. So when you multiply all these parameters and you add the remaining terms, and ultimately you will get the total surface area of the 5 sides of the boxes, right, which will be equal to 0.4 meter square. So this is the radiation heat transfer from the box. This is the formula which can be used to explain the radiation heat transfer from the box to the surface, and you have also studied this formula in the lectures. So the rate of radiation heat transfer is equivalent to the emissivity multiplied by the constant, and this constant is known as Boltzmann constant, and it has a specific units, and the AS is the surface area, and the TS to the power 4, which is the surface temperature, and in this case it is given as 55 degrees centigrade, and T surrounding to the power 4, which is the surrounding temperature, and in this problem you have to determine the surrounding temperature. So all the parameters are given in the question statement, and area you have just determined here. So you have to determine the surrounding temperature. So the radiation heat transfer rate is given, that is 100 watt, and emissivity is also given 0.95, and the Boltzmann constant, Stefan Boltzmann constant value is also given in the literature, and you can put the values as it is in this problem. And the next thing is the area, that is 0.48 meter square. And the last thing is that you have to convert this temperature into Kelvin, because in the Stefan Boltzmann constant the temperature units are in Kelvin. So you have to convert this degree centigrade into Kelvin by adding 273 Kelvin in that 55 degree centigrade. So after simplifying this equation, you will get the temperature of the surrounding, which will be equivalent to 296.3 Kelvin, or simply if you subtract 273 from this value in order to convert into degree centigrade, you will get the value that is 23.3 degrees centigrade.